Welcome to a journey through the deepest questions in physics, where reality might not be what it seems. In this video, we'll explore how modern quantum theory quietly points to a multiverse, not as science fiction, but as a natural consequence of the equations we trust every day. So take a deep breath, relax, and let's step into the calm, unfolding mystery of the quantum multiverse. Chapter 1. What is a multiverse, and why physicists take it seriously? The concept of the multiverse is one of the most fascinating and controversial ideas in modern science. For many, it sounds like science fiction. The notion that there could be countless other universes existing alongside ours, each with different versions of reality. Some might imagine alternate timelines, others might picture different laws of physics altogether. Surprisingly, this idea doesn't only come from imaginative storytelling, it also emerges naturally from serious scientific theories. In this chapter, we'll explore what scientists mean when they talk about the multiverse, and why many physicists consider it a legitimate possibility. While the concept stretches the imagination, its roots lie deep in established physics, particularly quantum mechanics. Let's start with a basic definition. Traditionally, the word universe refers to everything that exists, all matter, energy, space, and time. So how can there be more than everything? When physicists use the term multiverse, they're referring to the idea that what we see as our universe may just be one region or one instance within a much larger set of realities. These other universes may be entirely separate with no connection to ours, or they might be variations that split off from the same physical origin. There isn't just one kind of multiverse theory. In fact, there are several, each arising from different areas of physics. One of the earliest scientific suggestions came from cosmic inflation, the theory that the universe underwent a rapid expansion just after the Big Bang. According to many versions of this theory, inflation didn't end everywhere at once. Instead, it continued in isolated regions, creating bubble universes. Each bubble could evolve separately, forming its own laws of physics and particles. Our universe in this view is just one bubble among many in an eternally inflating space. Another potential source of a multiverse comes from string theory, a mathematical framework that attempts to unify all the known forces of nature. String theory doesn't describe just one universe. It allows for an incredibly large number of possible solutions. Each solution represents a different way that space and the physical laws can be arranged. Some estimates suggest there could be over 10 to 500 different ways the equations can play out. Each of these could correspond to a separate universe with its own unique version of reality. But perhaps the most directly relevant version of the multiverse, and the one we'll focus on throughout this video, comes from quantum mechanics, the science of the very small. In quantum physics, particles don't behave like tiny billiard balls. Instead, they exist in a blend of possibilities, called a superposition, until they are measured. At that moment, it seems like the system chooses one outcome. Traditionally, physicists explain this by saying the wavefunction, a mathematical description of all possible states, collapses when observed. But this explanation raises more questions than it answers. What exactly counts as an observer? Why should nature behave differently when someone is looking? To address these questions, some physicists proposed a different idea. The wavefunction never collapses at all. Instead, all possible outcomes happen, not in the same universe, but in different ones. This is known as the many worlds interpretation of quantum mechanics. It suggests that every time a quantum event has multiple possible results, the universe branches into parallel realities, each containing one outcome. Imagine flipping a quantum coin, one that lands both heads and tails until you check it. When you observe it, you see heads. But in another branch of the universe, someone just like you sees tails. Both outcomes occur, but in different realities. You are simply living in the version where one of those outcomes happened. This might seem like a wild idea, but it comes from taking quantum mechanics seriously, following the math without adding special rules. The equations that describe particles never say that only one outcome happens. They describe the evolution of all possible outcomes at once. So why don't we see these other universes? Why can't we detect them or travel between them? The reason lies in a process called decoherence. In quantum systems, superpositions can interfere, like ripples on a pond combining and canceling. But when a quantum system interacts with its surroundings, for example, air molecules, photons, or even heat, that interference breaks down. The system becomes classical, with distinct outcomes that no longer affect one another. Each branch becomes isolated, invisible to the others. This process happens incredibly fast, even at microscopic scales. It's why we don't see particles in two places at once in everyday life. The interaction with the environment splits the quantum branches so quickly and thoroughly that we only ever observe one path. Still, many people ask, if these universes can't be accessed, are they real? Can this idea be considered scientific if it can't be tested? That's a fair concern. In science, testability is important, but theories are also judged by how well they explain what we observe and how simply they do so. The many worlds interpretation doesn't require new physics or arbitrary rules. It just extends the quantum equations to everything, including observers. It provides a consistent explanation without needing a mysterious collapse mechanism. Even though we may not be able to prove the multiverse directly, we can evaluate whether the theories that predict it are successful in other ways. For example, inflation theory makes predictions about the distribution of galaxies and the cosmic microwave background, predictions that have matched observations very well. String theory is harder to test, but it's being studied for its potential to unify known forces. Likewise, quantum mechanics, including the version that leads to the multiverse, is one of the most successful theories in all of science. It's been confirmed in countless experiments, and it underpins technologies like lasers, computers, and MRI machines. There are even some indirect clues that suggest a multiverse might help explain puzzling features of our own universe. One such clue is the fine-tuning problem. The fundamental constants of nature, such as the strength of gravity or the mass of the electron, seem precisely balanced to allow stars, atoms, and life to exist. If these numbers were slightly different, our universe might be lifeless. In a multiverse, this becomes less surprising. If there are many universes with different parameters, it's not shocking that we find ourselves in one where the conditions happen to be right. Of course, this isn't definitive proof, but it's another reason physicists take the idea seriously. It offers a potential solution to questions that otherwise seem unlikely or arbitrary. To sum up, the multiverse is not a fringe idea. It's a logical consequence of theories that are already well supported: quantum mechanics, inflation, and string theory. It doesn't require new forces or extra assumptions. It simply asks, what happens if we take the known laws of physics at face value? If quantum systems really evolve through all possible outcomes, and if each of those outcomes becomes independent through decoherence, then it follows that the universe doesn't just make choices, it makes copies. Not imaginary ones, but real, physical, non-interacting branches that unfold according to the same rules we observe here. In this light, the multiverse isn't a wild fantasy. It's one of the most straightforward interpretations of quantum physics we have. And that's why physicists are listening. Chapter 2: The Quantum Origin, Schrödinger's Cat and the Birth of Many Worlds. To understand where the idea of the multiverse truly begins, we must revisit one of the most famous and paradoxical thought experiments in all of science: Schrödinger's cat. Though it might seem whimsical at first, a cat, a box, and a deadly mechanism, it reveals the deep tensions at the heart of quantum mechanics. At its core lies a question: what happens between the moment something is uncertain and the moment we observe the outcome? In the 1930s, physicist Erwin Schrödinger proposed this scenario to highlight what he saw as a problem with the prevailing understanding of quantum theory. He imagined placing a cat in a sealed box with a radioactive atom, a Geiger counter, a vial of poison, and a trigger mechanism. If the atom decays, a quantum event with a probabilistic outcome, the Geiger counter detects it, breaks the vial, and kills the cat. If it doesn't decay, the cat remains alive. According to quantum theory, until we open the box and look inside, the system exists in a superposition of both states, decay and non-decay. And therefore, in some strange sense, the cat is both dead and alive. While Schrödinger intended the scenario as a critique, it became one of the most important illustrations of quantum weirdness. The idea that a system, even something as large as a cat, could be both dead and alive at the same time is deeply unsettling. Yet it flows naturally from the mathematics of quantum mechanics. This leads to a critical point. The strangeness isn't in the cat itself, but in how we interpret what quantum theory tells us about measurement and observation. In traditional or Copenhagen interpretations of quantum mechanics, the wave function collapses when a measurement occurs. The cat becomes either alive or dead the moment someone opens the box and looks. But this raises troubling questions. What counts as a measurement? Does consciousness cause collapse? If the universe contains only quantum systems, then who or what decides the outcome? This is where the many worlds interpretation offers a radical and elegant alternative. Proposed by physicist Hugh Everett in 1957, the idea was simple but profound. The wave function never collapses. Instead, it evolves according to the rules of quantum theory, continuously and deterministically. Every possible outcome happens, and the universe splits, branching into multiple non-communicating realities. When you open the box, you don't force the universe to choose between a live or dead cat. Instead, the universe divides. In one branch, you see a live cat. In another, you see a dead one. Both outcomes occur, and you are part of both. Your own state becomes entangled with the state of the cat, creating parallel experiences in parallel realities. This process is called quantum branching, and it forms the foundation of the multiverse as described by quantum mechanics. Unlike science fiction depictions, these branches don't interact or collapse back into one. They continue on independently, like threads in an ever-growing tapestry. Every time a quantum event with multiple possible outcomes occurs, which happens constantly at the microscopic level, the universe branches again. Importantly, this doesn't mean that decisions or human thoughts directly cause the universe to split. The branching happens at the level of physical interactions, a photon hitting a molecule, a particle decaying, a spin measurement being made. You, as a conscious observer, are simply carried along by one of the resulting branches, the one that aligns with the outcome you observe. The math behind this is clean and requires no additional rules. The wave function evolves in a linear fashion, and measurement is just another interaction, not a special, mysterious process. In this sense, the many worlds interpretation is actually simpler than alternatives that require a collapse. It treats observers like any other quantum system, made of particles, governed by the same laws. To appreciate the significance of this, consider how it resolves some of the paradoxes that plague standard interpretations. In the Copenhagen view, when does the collapse happen? Does it require a conscious mind? If a tree falls in a quantum forest and no one observes it, is there sound? These philosophical puzzles are sidestepped by many worlds, which doesn't rely on the act of observation at all. Every possibility plays out, every path continues. Still, this raises new questions. If all outcomes happen, why do we experience only one? Why do we perceive a single consistent reality rather than a blur of all possible versions? The answer lies in quantum decoherence, the process by which quantum systems lose their coherence through interaction with their environment. When a quantum system, such as a cat or an atom, interacts with something else, like air molecules or light, its possible states become entangled with those of the environment. The interference between different outcomes vanishes. This makes the branches effectively independent. Decoherence doesn't destroy the other possibilities, it just makes them unreachable. Once a system decoheres, it no longer shows interference effects. In other words, the worlds split, and from that point on, they evolve separately. Now, let's return to Schrödinger's cat. Before the box is opened, the radioactive atom is in a superposition of decayed and not decayed. Because the poison and the cat are linked to this outcome, the whole system, atom, detector, poison, cat, is in a superposition. When the observer interacts with the box, they become part of this entangled system. The result is not a single reality emerging, but rather a branching of the observer into multiple versions, each witnessing a different outcome. This branching is not something we can perceive directly. We experience only the outcome within our branch. But quantum theory, when applied universally, tells us that the others must exist as well. They are not imaginary, nor merely theoretical. They are physical outcomes governed by the same laws. One important clarification is that this idea that the wave function evolves without collapse is not a rejection of experimental results. All interpretations of quantum mechanics agree on the outcomes of experiments. What differs is how we interpret the meaning of those outcomes. In many worlds, the branching is not something we detect directly, but something inferred from how consistently the math describes physical systems. In fact, many worlds avoids the need to define what constitutes a measurement at all. Consider a laboratory experiment in which a physicist measures the spin of an electron. The electron is initially prepared in a state that is a superposition of spin up and spin down. Upon measurement, in the many worlds view, the universe branches. One version of the physicist records spin up, the other records spin down. Each observer remembers having seen only one outcome, their own, but the full picture includes both. This interpretation is testable only in the sense that it predicts the same statistical results as conventional quantum mechanics. That's part of the challenge. It cannot currently be distinguished by experiment from the standard collapse-based models. However, its appeal lies in conceptual clarity and mathematical simplicity. It doesn't require a special mechanism for measurement. It doesn't elevate observers to a privileged status. It simply lets the equations run. Critics argue that, without a way to detect the other branches, the many worlds interpretation is metaphysical, not truly scientific. But defenders counter that rejecting it often requires adding unexplained postulates, like wavefunction collapse, which themselves cannot be derived from known physics. In this light, many worlds may not be a leap of imagination, but a refusal to bend the rules to suit human intuition. Moreover, the consequences of this view ripple far beyond atomic measurements. They imply that every physical interaction, every photon absorbed, every molecule excited, is a site of potential branching. The multiverse, then, isn't something far away. It's here, now, unfolding all around us, in a way that is silent and undetectable, but perhaps unavoidable. There's also a growing interest in using quantum computing to test the structure of quantum theory more directly. While these technologies won't detect other universes, they may force us to confront the logic behind interpretations. Quantum computers operate by leveraging superpositions and interference, concepts that are natural in many worlds. As we better understand how to manipulate quantum information, we may also refine how we think about quantum reality itself. One might ask why this matters. If we can't reach other branches, and if they don't affect us, why bother talking about them? The reason lies in the foundations of physics. Science isn't only about predicting outcomes, it's also about understanding why the world behaves the way it does. If many worlds is correct, then the reality we observe is just a small slice of a much larger structure. That structure, the full wave function of the universe, evolves smoothly and predictably. It doesn't depend on when someone opens a box or blinks their eyes. It just is. There is, of course, a hint of the existential in all this, not in a mystical sense, but in a deeply physical one. The idea that countless versions of us may exist, each branching with every quantum event, is both sobering and humbling. It suggests that what we call reality is not a single thread, but a densely woven fabric of possibilities. Yet even in this view, your experience remains your own. You are not lost in the multiverse. You are one outcome, fully real, fully valid, governed by the same quantum rules as every other. Chapter 3. The moment you split, how choices create parallel versions of you. In the quantum world, every decision is not merely a metaphorical fork in the road. It's a physical, branching event governed by the laws of quantum mechanics. While our everyday experience suggests that we live in a single, continuous timeline, the implications of quantum theory tell a different story. They suggest that what we perceive as a single chain of events may, in fact, be just one thread in a vast and constantly branching structure, a multiverse of possibilities. To understand this branching process, we must first revisit the nature of quantum superposition. In classical physics, a system is in one definite state at a time. A coin is either heads or tails, a light is either on or off. But in quantum mechanics, systems can exist in combinations of states, what we call superpositions. A quantum coin can be in a state that is both heads and tails simultaneously, at least until we observe it. Observation, or more precisely, interaction with an external environment, leads to a breakdown of this superposition in our experience. However, if we take the many worlds interpretation seriously, as many physicists do, this isn't because the superposition collapses. Instead, each possible outcome continues to evolve, just in separate, non-communicating branches of the universe. This means that at the moment a quantum event with multiple outcomes occurs, reality itself splits. Each outcome is realized, but in a different version of the universe. And crucially, if a conscious observer is involved, that observer also becomes part of the branching process. You are not simply watching reality divide, you are dividing along with it. Let's ground this in a practical example. Imagine you're participating in a quantum experiment where you measure the polarization of a single photon. The photon is prepared in a superposition of horizontal and vertical polarization. When you perform the measurement, quantum mechanics predicts there's a 50% chance you'll find it horizontal, and a 50% chance it will be vertical. In the traditional view, you perform the measurement and see one result, say horizontal. The wave function is said to collapse, and the other possibility disappears. But in the many worlds framework, both outcomes occur. The universe splits. In one branch, you see horizontal, in the other, you see vertical. Both versions of you exist, each remembering a single outcome. What makes this fascinating and scientifically profound is that this branching doesn't only happen in physics labs. Quantum events are everywhere. The thermal motion of molecules, radioactive decay, quantum tunneling, the firing of neurons in your brain, all involve elements of uncertainty at the quantum level. And if every such event causes a split, then branching is happening constantly, all around us. You might wonder, does this mean every time I choose cereal over toast, or turn left instead of right, I create another version of myself? Not exactly. The many worlds interpretation is not about free will or human choices in the philosophical sense. It's about the branching of physical outcomes. But because our thoughts and decisions are the result of brain activity, And because brain activity is ultimately based on the behavior of atoms and ions and neurotransmitters, which are subject to quantum laws, it's possible that the branching process extends into the decisions you make. Of course, we don't perceive this. Our experience is always of a single stream of consciousness, moving smoothly from one moment to the next. But this is a matter of perspective, not of reality. Each version of you in a branch perceives their path as continuous and self-contained. They have memories, intentions, and a sense of identity, even though countless other versions, differing by tiny or major events, exist in parallel. One of the most intriguing aspects of this model is how it preserves the notion of probability. If everything happens, why do we experience some outcomes more frequently than others? Why do quantum experiments follow statistical patterns? The answer lies in the mathematical structure of the wave function. The square of the amplitude of each outcome determines its weight, not in the sense of importance, but in terms of how much of the wave function's stuff occupies that branch. When you repeat a quantum experiment many times, the proportion of branches where a particular result occurs matches the expected probability. In other words, even in a deterministic branching universe, statistics still emerge in the observed data. This process is known as the Born rule, and it's a cornerstone of quantum mechanics. One of the ongoing discussions in theoretical physics is how, or whether, the Born rule can be derived from the structure of the branching multiverse itself, without assuming it as an extra postulate. Some researchers argue that the rule arises naturally from rational decision-making under uncertainty, as seen from within the multiverse. It's also worth noting that these branches are not created in the sense of needing energy or space. They are implicit in the structure of the quantum wave function, which describes all possibilities simultaneously. The evolution of the wave function is governed by deterministic equations. Nothing is added or removed. The entire multiverse unfolds as a consequence of those equations. Despite the mind-bending implications, this model is remarkably elegant. It requires no extra rules, no mysterious collapse, no special role for consciousness. It treats humans, measuring devices, cats, and electrons with the same physical principles. And it suggests that the universe doesn't merely contain uncertainty. It is uncertainty, playing out in full. We might never be able to detect or interact with other branches. Decoherence ensures that each branch evolves independently without interference. The information that differentiates the branches becomes locked in complex correlations with the environment, inaccessible and practically irreversible. In a sense, the multiverse is a solution that hides itself. Yet even if hidden, its effects are implied. The very consistency of quantum experiments, the structure of quantum computing, and the reliability of the Born rule all point toward a reality where outcomes do not collapse, but diverge. Let's consider what this means for time and memory. In a branching universe, each copy of you continues with its own version of the past, present, and future. The act of measurement or decision not only creates a new timeline, but also a new subjective continuity. Memory functions normally within each branch. You recall having made a choice, unaware that another version of you made a different one. This self-consistency is crucial. It's what allows the illusion of a singular, continuous existence even as branching occurs. There is no conflict or overlap between versions. Each has its own environment, its own body, and its own trajectory. The rules of physics keep branches isolated after decoherence, preventing paradox or contradiction. From a computational standpoint, some theorists compare the branching multiverse to a kind of massively parallel processing, like a quantum computer operating on many inputs at once. Every possibility is computed, but each observer receives only one output. The others exist, but in different computational pathways, inaccessible and self-contained. Interestingly, some proposals in cosmology suggest that the universe might have a finite quantum state space, a limited number of fundamental degrees of freedom. If true, this could imply that the multiverse is not infinite, but instead vast and intricate within a constrained framework. Other ideas suggest the opposite, an infinite number of branches, producing every possible configuration of particles and outcomes, including copies of Earth, of this moment, and of you. And what of identity? If versions of you exist in other branches, are they you? Do they share your consciousness? The many worlds framework doesn't provide direct answers to these philosophical questions. It treats all outcomes as physically real, but it doesn't define the nature of self. Most physicists would say that identity, like memory and perception, is confined within a single branch, a single continuity of observation. Yet there's a subtle existential echo in all this, that the universe doesn't just allow possibilities, it realizes them. Every outcome that can happen does. And every version of you that can exist does too somewhere. It's not about destiny or fate or metaphysics. It's about what the mathematics of quantum physics seems to describe when taken seriously and without exceptions. This doesn't mean that your choices don't matter. Quite the opposite. Within your branch, your actions shape your future. The multiverse doesn't negate responsibility or agency, it reframes it. It shows that while all outcomes may exist, you still live each one moment by moment, decision by decision. Your world, this world, is as real as any other. And though countless other branches might exist, you don't need to worry about them. They aren't ghosts or shadows. They're just other paths through a deeper landscape, one you navigate unknowingly every time quantum uncertainty meets observation. Chapter 4. The wave function never collapses, and that changes everything. At the heart of quantum mechanics lies the wave function, a mathematical object that contains all the information about a quantum system. Whether we're describing an electron, a photon, or an entire atom, the wave function tells us the range of possible states the system could be in and how likely each is. It's the central entity in quantum theory, and it evolves smoothly over time according to a well-established equation. But what happens when we perform a measurement? In standard quantum mechanics, we're told that the wave function collapses, that all the possibilities encoded in the wave function disappear except for the one we observe. This collapse is instantaneous, and it appears to break the otherwise smooth, continuous evolution of the system. It introduces an exception, a moment where the rules of the universe seem to change based on whether an observation is made. For decades, physicists accepted this collapse as a necessary but mysterious part of quantum theory. It worked. It produced results that matched experiments to astonishing precision, but it left fundamental questions unanswered. What counts as an observation? Does the universe behave differently when someone is watching? Is collapse a physical process or just a mathematical shortcut? This is where the many worlds interpretation offers a powerful and elegant alternative. Instead of proposing that the wave function collapses upon observation, it posits that the wave function never collapses at all. It continues to evolve smoothly, deterministically, and universally. All the possibilities described by the wave function continue to exist, just not all in the same universe. From this perspective, a measurement is not a collapse, but an interaction, one quantum system entangling with another. When a photon hits a detector, or when a scientist records a result, the system becomes entangled with its surroundings. The wave function doesn't reduce to a single outcome, it expands to include all outcomes, each realized in a separate branch of the universe. Let's take a practical example. Suppose a radioactive atom has a 50% chance of decaying in the next minute. The wave function describing that atom is a superposition, decayed and not decayed. When a detector checks the atom after 1 minute, The conventional view says the wave function collapses. The atom is either decayed or not. But in the many worlds view, both outcomes happen. The detector becomes entangled with both states of the atom, creating two branches, one where the decay is recorded and one where it is not. This approach solves a long-standing problem in quantum theory, the so-called measurement problem. In standard quantum mechanics, the act of measurement is given a special status. It's treated differently from all other physical processes, but that distinction is arbitrary. Why should a quantum particle follow one set of rules until someone looks and then obey a different set the moment it is observed? By eliminating collapse, the many worlds interpretation removes this inconsistency. It treats measurements as just another form of quantum interaction, no different in principle from a collision between particles or a chemical reaction. The wave function evolves continuously. There are no abrupt jumps, no mysterious interruptions, no special roles for observers. The same rules apply at every scale, from atoms to people to planets. This continuity has profound implications. It suggests that reality is fundamentally quantum, not classical with quantum features layered on top, but quantum all the way up. The classical world we experience, the world of definite positions, outcomes, and events, is a result of decoherence and perspective, not an underlying truth. What we call reality is just one path through the full branching evolution of the wave function. One of the challenges in communicating this idea is that it conflicts with everyday intuition. We don't experience ourselves splitting. We don't see particles in multiple places at once. We experience one outcome, one path, one timeline. But this too is explained by the theory. Once a measurement-like interaction happens and decoherence takes over, the branches of the wave function become non-interfering. Each branch contains a version of the observer who only sees their own result. In practical terms, the universes don't interact. You can't hop between them. There's no way to communicate with your other selves. Decoherence ensures that each branch evolves independently, and the information that defines the branching is effectively lost to the environment. The branches are real, but isolated. Still, this interpretation remains controversial. One of the reasons is its sheer scale. If every quantum event produces a branching, then the number of parallel realities is unimaginably large, possibly infinite. Critics argue that this is an extravagant hypothesis, multiplying entities beyond necessity. But supporters counter that it's not adding complexity, it's removing arbitrary rules. Instead of assuming collapse, they follow the math wherever it leads. And the math leads to branching. The Schrödinger equation, the foundational rule for how wave functions evolve, has no provision for collapse. It describes smooth, unitary evolution. When collapse is added in standard interpretations, it must be done manually, with no underlying mechanism to support it. This makes the collapse postulate not only mysterious, but also inconsistent with the rest of the theory. Some have attempted to develop collapse-based models that include new physics, spontaneous collapse theories, objective reduction models, and others. These approaches seek to explain wave function collapse as a real physical process. But none has yet been confirmed by experiment, and many face significant challenges in maintaining consistency with known quantum phenomena. In contrast, many worlds requires no such extensions. It assumes only that the wave function, which is already a central part of quantum mechanics, describes reality completely, and that its evolution is always governed by the same equation. The universe doesn't need to do anything special when we look at it. It just continues being quantum. To many physicists, this is appealing. It brings quantum theory in line with the rest of physics, where laws are continuous and universal. It avoids the awkwardness of defining observers and measurements, and it opens the door to a richer understanding of reality, one that is broader, stranger, and perhaps more complete. Let's reflect for a moment on what this means. If the wave function never collapses, then what we call now is only a slice through a much larger structure. Every possible outcome that could have happened from past events still exists, not just as a counterfactual, but as a branch of the universe evolving in its own direction. Every possible outcome of the future also exists in potential, waiting to be realized in some version of reality. This doesn't mean that the world is chaotic or that anything goes. The laws of physics still apply with mathematical precision, but they apply to all outcomes, not just the one we perceive. Reality, in this view, is not a line. It is a constantly branching tree. You exist as one path through that tree. Your memories, your sensations, your experiences, all are real within your branch. You don't feel the branching, and you don't need to. From your perspective, events unfold in a coherent, logical way. But the deeper truth is more complex. Beneath the surface of your everyday world lies a quantum structure of staggering breadth. Let's also consider the role of experimental support. While the many worlds interpretation cannot yet be directly tested, since we have no way of accessing the other branches, it makes the same predictions as standard quantum mechanics in every experiment ever performed. Its advantage lies in theoretical simplicity and philosophical coherence. By trusting the formalism of quantum mechanics as complete, many worlds avoid inconsistencies and unexplained rules. Furthermore, modern developments in quantum computing add weight to this view. Quantum algorithms such as Shor's algorithm and Grover's search make use of interference between computational branches. While these branches don't map directly onto many worlds' realities, the conceptual overlap has led many physicists to reconsider how quantum computation relates to parallel processing. The idea that many computations are carried out simultaneously, though not directly observable, aligns well with the idea that many realities unfold in parallel. This doesn't mean quantum computers prove the multiverse, but they do highlight how much more intuitive quantum mechanics becomes when we accept the wave function as real and continuous. Not something to be collapsed or ignored, but something to be understood as the core structure of nature. As the field progresses, physicists continue exploring alternative models, from hidden variable theories to objective collapse frameworks. But no experimental evidence has yet disqualified the many worlds view, and many researchers see its mathematical purity as a guiding light. It may not be the only answer, but it remains one of the most logically consistent interpretations of the quantum world. And that brings us to the quiet revolution. That reality might never collapse, and we might never be confined to a single thread of possibility. You are here now, following one path, but countless others unfold around you, unseen, untouched, yet governed by the same elegant rules. Your experience is not diminished by this possibility, it is enhanced by it. The absence of collapse doesn't erase your story, it simply places it within a wider context. A universe that doesn't destroy possibilities, but preserves them. In a world where the wave function never collapses, nothing is truly lost. Every outcome has a place, every path a space. And in the calm stillness of this scientific truth, there's something quietly profound, that even the smallest particle obeys a law that leaves room for everything. Chapter 5. Quantum Decoherence, Why the Other Universes Stay Hidden. If the universe really branches every time a quantum event has multiple possible outcomes, then a natural question arises. Why don't we see any of these other branches? Why is our experience limited to a single outcome if countless versions of reality are constantly unfolding? The answer lies in a crucial concept within quantum mechanics known as decoherence. This phenomenon plays a central role in explaining how the classical world we observe emerges from the underlying quantum reality. It also provides a compelling explanation for why the other branches of the multiverse remain hidden from view. To understand decoherence, we first need to revisit how quantum systems behave. At the smallest scales, electrons, atoms, photons, particles don't have well-defined positions or velocities. Instead, they exist in superpositions, mixtures of all possible states. These superpositions allow for strange phenomena like interference patterns and entanglement. However, these effects are fragile. When a quantum system is isolated, shielded from all interactions, it can maintain coherence, meaning the various components of its wave function continue to interfere with one another. But in the real world, perfect isolation is nearly impossible. Quantum systems are constantly interacting with their environments, with stray photons, air molecules, thermal vibrations, or even the measuring apparatus itself. These interactions entangle the quantum system with its surroundings. As a result, the system's wave function becomes part of a much larger wave function, one that includes the environment. When this happens, the original superposition no longer behaves as a single unified state. Instead, the different components of the superposition evolve independently, unable to interfere. This is decoherence. Importantly, decoherence is not the same as wave function collapse. It doesn't destroy any of the branches or choose a single outcome. Rather, it prevents the different branches from interacting or influencing one another. From the perspective of an observer within one branch, it appears as if only a single outcome has occurred. But from the perspective of the universal wave function, all outcomes are still present, just separated beyond the possibility of interference. Let's make this more concrete with an example. Suppose a quantum particle is in a superposition of two paths, left and right. If it's perfectly isolated, we can set up an experiment to observe interference, a pattern that results from the overlapping of the wave function's components. But if the particle interacts with the environment, say, a photon bounces off it, the coherence is lost. The environment now knows which path the particle took, even if we never measure it directly. The interference pattern disappears. From our perspective, it's as if the particle took one definite path. But the underlying quantum description still includes both, now entangled with the environment. In the many worlds interpretation, this loss of interference corresponds to a branching event. One branch contains the particle taking the left path, another contains the particle taking the right. The environment, including the measuring device and the observer, becomes entangled with the outcome. Each resulting branch evolves separately. There's no interference because the information that would allow it has been dispersed into the environment, effectively out of reach. This environmental entanglement is why we don't see quantum superpositions in daily life. Macroscopic objects like chairs, apples, or people are composed of enormous numbers of particles, each of which is constantly interacting with the surroundings. Any superposition involving such objects decoheres almost instantly. The coherence time, the interval over which interference could occur, is vanishingly short. So while superpositions and branching still occur, we experience only one result. Decoherence provides a bridge between quantum and classical physics. It shows how the strange, probabilistic world of the very small gives rise to the definite, reliable world of the everyday. It's not that quantum mechanics stops applying. It's that the quantum effects become effectively hidden, buried in complex entanglement with the environment. What makes decoherence especially compelling is that it has been confirmed by experiment. Scientists have observed and measured coherence and decoherence in systems like trapped ions, superconducting qubits, and molecules. In carefully controlled environments, they can maintain coherence long enough to study quantum interference. But even the slightest disturbance, a stray photon or thermal fluctuation, causes decoherence. These results match theoretical predictions with extraordinary accuracy. In recent years, this understanding has become central to the field of quantum computing. Quantum computers rely on maintaining coherence between quantum bits, or qubits, to perform calculations. Decoherence is their greatest enemy. As soon as the qubits interact too much with the environment, the quantum information is lost, and the computation fails. This challenge has led to the development of techniques like quantum error correction and decoherence suppression, which aim to protect fragile quantum states and extend coherence times as long as possible. But while decoherence explains why we don't observe other branches of the multiverse, it also highlights that they are not destroyed. They remain real within the total wave function. The information isn't lost, it's just entangled with degrees of freedom we no longer have access to. From the global perspective, the wave function still contains all outcomes. It's just that the parts no longer talk to each other. It's worth noting that decoherence alone doesn't select a preferred outcome. It explains why branches become independent, but not why we find ourselves in one particular branch. In many worlds, this is simply a matter of perspective. The observer becomes part of the entangled system, and their subjective experience continues in one branch, with no awareness of the others. Each version of the observer experiences their own outcome as unique, but every version exists. Some critics argue that decoherence, while powerful, doesn't fully resolve the measurement problem. After all, the outcome still appears definite to an observer. But in the many worlds view, this is not a problem, it's an expected feature. The definiteness of outcomes arises from entanglement and perspective. There's no need to collapse the wave function to explain what we see. What we see is one slice of a much larger, branching structure. To appreciate how deeply decoherence governs our experience, consider that even your thoughts, the result of neural activity, are influenced by quantum events at microscopic levels. However, because your brain is a warm, wet environment with immense environmental interaction, decoherence acts rapidly. Every neural signal, every firing of a synapse, every biochemical interaction is bathed in countless interactions with surrounding particles. The coherence required for quantum interference is lost almost instantly. In this way, decoherence not only shapes what we observe externally, but it defines the boundaries of what is even possible to experience internally. It is the filter through which quantum potential becomes classical actuality. It's why you feel singular, grounded, and located in one timeline, even as physics tells us that countless timelines are playing out. Interestingly, researchers continue to explore whether any traces of decoherence can be observed at larger scales. In laboratory settings, Schrödinger cat states, superpositions of large systems have been realized with tiny mirrors, molecules, and quantum circuits. These experiments test how quickly decoherence sets in and how robustly quantum behavior can persist. As expected, the larger and warmer the system, the faster decoherence destroys coherence. This supports the idea that classicality is not fundamental, but emergent. In this context, the classical world is not fundamental. It is emergent, a consequence of scale, complexity, and the overwhelming presence of environmental interactions. Decoherence explains how the sharp edges of reality appear, even though beneath them lies a blur of quantum possibility. Some physicists have proposed that decoherence might play a role in the arrow of time, the reason why we remember the past but not the future. As systems become more entangled with their environments, they lose information that could, in principle, be reversed. Entropy increases, and with it, a sense of forward motion. This is speculative, but it illustrates the reach of decoherence. It touches not only our perceptions of space and substance, but also of time and continuity. The most profound implication, perhaps, is that the multiverse doesn't need to hide itself. It is hidden by the very mechanism that makes reality seem coherent to us. We don't witness the splitting because the branches are sealed off by decoherence. We don't meet other versions of ourselves because we have decohered from them, not destroyed, not erased, just separated by a boundary deeper than space, the boundary of entanglement and environmental complexity. And so, as you move through your day, watching sunlight scatter off leaves, listening to the subtle echoes of a room, or sensing the weight of memory, all of it is filtered through decoherence. You are not a passive witness of a singular world. You are a coherent observer inside one thread of a branching universe. And though you may never see the others, physics assures us they are there, silent, parallel, and just as real. Chapter 6. Branching at the smallest scale. How often does the universe split? When people first hear about the multiverse implied by the many worlds interpretation of quantum mechanics, they often imagine a universe splitting only during major events, the outcome of a coin toss, a measurement in a laboratory, or a life-changing decision. But quantum mechanics doesn't operate only on the scale of human perception. It governs everything, from the tiniest particles to the largest structures in the cosmos. To understand the true scope of the multiverse, we must look beyond macroscopic events and examine the level at which branching really occurs. It turns out that the universe may split not just during rare or important moments, but constantly, and at scales so small that they defy imagination. At the foundation of this idea is the fact that quantum interactions are probabilistic. Electrons don't have precise positions or paths. Photons don't follow clean trajectories. Instead, particles exist in superpositions, combinations of many possible outcomes, and when they interact with other particles, those superpositions evolve, split, and become entangled. According to the many worlds view, each of these interactions results in a branching event. Let's take a simple example. A single photon traveling through a semi-transparent mirror. There is a 50% chance the photon will be reflected and a 50% chance it will pass through. In classical terms, we'd say it takes one path or the other. But in quantum mechanics, until the photon is detected, it is in a superposition of both outcomes. And when the photon reaches a detector, any detector, the entire system, including the mirror, the photon, and the detector, enters into an entangled superposition. In many worlds, this is a branching point. One branch contains the universe where the photon was reflected. Another contains the universe where it passed through. Each outcome is realized in a separate branch of reality, and each continues independently from that point forward. This isn't just a theoretical abstraction. Quantum electrodynamics, the most precisely tested theory in physics, is based on these superpositions and interactions. Every interaction between charged particles, every emission or absorption of a photon, every quantum fluctuation in the vacuum is governed by probabilities and wave functions. That means, in theory, branching is happening on scales of space and time that are incomprehensibly small. So how often does the universe split? The answer depends on what level of granularity we choose. If we define a split as any interaction that leads to decoherence and entanglement, then branching is virtually continuous. Every moment, every location in space, every quantum interaction produces new, non-interfering branches. Consider a volume of air in a room, a space filled with countless gas molecules bouncing around, colliding, exchanging energy. Each of these collisions is, at a microscopic level, a quantum event. Each could, in principle, be associated with a range of possible outcomes, slightly different trajectories, speeds, or scattering angles. Every one of these differences corresponds to a potential branching, with the environment becoming entangled with each result. And because each of these interactions occurs at rates of billions or trillions per second, even in a small volume of space, the number of branches accumulates rapidly. In fact, the number of possible histories that result from these interactions grows exponentially. Over time, this produces an almost inconceivable number of distinct branches, each representing a slightly different version of reality. This is not to say that every possible event happens with equal frequency or equal weight in the wave function. Quantum mechanics assigns amplitudes to each outcome, which determine their relative probabilities. Most branches may have negligible amplitude and thus an extremely low likelihood of being experienced by an observer, but they still exist within the structure of the wave function, and from the perspective of many worlds, they are as real as any other. Importantly, not every split corresponds to a dramatically different world. Many of these branches differ only in imperceptible details: the spin of a single electron, the path of a single photon, the vibration of a single molecule. The vast majority of branches are nearly identical to each other, at least for a while. It is only over time, as differences accumulate and compound, that some branches diverge into meaningfully different histories. This insight leads to an interesting conclusion. Most of the multiverse may be filled with universes that are almost, but not quite, like ours. In one, a cosmic ray hit a silicon atom in your brain 1 nanosecond earlier. In another, a grain of dust settled half a micron to the left. These seem trivial, and perhaps they are, but they remind us that reality is not built from absolute events, but from continuous interactions on all scales. One of the places where this branching becomes especially evident is in controlled quantum experiments. In laboratories around the world, physicists use beam splitters, interferometers, and entangled particles to explore the probabilistic nature of reality. These experiments demonstrate how superpositions and branching occur at the level of individual particles. When detectors are placed or removed, when interference is allowed or disrupted, the results change. Not because the particles make choices, but because the quantum systems evolve differently depending on the measurement setup. In these experiments, the transition from quantum uncertainty to classical definiteness occurs not through collapse, but through entanglement with a wider system: the measurement device, the environment, and ultimately the observer. Each time this happens, branching occurs. And because modern experiments involve hundreds, thousands, or even millions of particles, the number of branches grows rapidly. Even so, it's crucial to emphasize that these branches are not stacked atop each other like slices of paper, nor are they layered through space like parallel universes in science fiction. They are configurations of the wave function, distinct, non-interfering components that evolve according to the same equations, but which cannot communicate or exchange information once decoherence has occurred. Some physicists have tried to calculate how many branches might exist after even a short period of time. These calculations vary depending on assumptions about interaction scales, coherence thresholds, and system size, but all suggest that the number is staggeringly large. In a few seconds, even a relatively simple system like a dust particle interacting with sunlight can branch into a number of distinct quantum histories that far exceeds the number of atoms in the observable universe. This doesn't imply that the multiverse is chaotic or unstructured. Quite the opposite. The branching follows the mathematical rules of quantum mechanics: smooth, deterministic, and guided by probability amplitudes. Every branch follows from a previous one. There are no jumps, no paradoxes, no contradictions. The wave function evolves like a river splitting into tributaries, each path consistent, each outcome natural. Over time, as branches multiply and spread, the structure of the multiverse becomes richer. Some branches may lead to radically different worlds, the decay of a nucleus triggering a sequence of events that alters history. Others may remain nearly indistinguishable from their neighbors. But all are outcomes of the same fundamental process: unitary evolution without collapse. You might wonder what this means for us, not just as observers, but as participants in this ever-branching structure. It means that you, as a conscious system, are continuously entangling with the world around you. Every time you observe, act, or think, at least insofar as those actions depend on physical interactions, you become part of a specific quantum branch. The version of you in another branch did something slightly different, looked left instead of right, spoke instead of remaining silent, took a step that led to a different thought, a different path. You will never meet these other versions. Decoherence has sealed them away, made them inaccessible. But they are there, embedded in the fabric of the universal wave function. Not fictional, not imaginary, just causally separated by the branching flow of quantum interactions. And so, we arrive at a final reflection. The universe doesn't split in dramatic flashes or cosmic decisions. It branches quietly, billions of times per second, at scales too small to see, in ways too subtle to feel. And yet, those branches contain everything. Every outcome, every variation, every possibility permitted by physics. You are part of this, not as a detached observer, but as an active participant. Each moment, each breath, each glance becomes part of the branching. Your life, like all lives, is one line in a vast and ever-dividing structure. And though you may never sense the others, the rules that shaped your world shaped theirs too. In this vision, reality is not a single film strip playing out in one direction. It is a library of possibilities, constantly updating, constantly expanding, written not by fate, but by quantum logic. And you right now are reading one page of that library. Turn the page, and a new branch begins. Chapter 7. Does probability still make sense in a multiverse? In our everyday world, probability is a familiar concept. We use it to describe the chance of rain tomorrow, the odds of winning a game, or the likelihood of a particle being found in a certain location. In classical physics, probability reflects ignorance, our lack of precise knowledge about a system. If we knew the position and velocity of every particle, we could, in theory, predict everything that would happen. But in quantum mechanics, probability is something deeper. Even with complete knowledge of a system's wave function, the mathematical object that encodes all possible outcomes, we can't predict a single definite result. Instead, we get a set of probabilities. A particle may be here or there, but not with certainty. Even when a system is prepared identically and measured repeatedly, the results vary, and all we can do is assign likelihoods. This framework works beautifully in standard quantum mechanics. But in the many worlds interpretation, a puzzle arises. If all outcomes occur, each in a different branch of the multiverse, then what does it mean to talk about probability at all? After all, probability usually assumes that only one outcome happens, and the rest don't. You roll a die and get a 4. The chance of rolling a 6 was real, but didn't materialize. But in many worlds, every side of the die is rolled. Every possible result plays out in a separate branch. So if nothing is excluded, what role does probability serve? At first glance, it might seem that probability loses its meaning in a multiverse. If every possible outcome is realized, does it still make sense to say one outcome is more likely than another? Why should we expect the frequencies we observe to match the probabilities calculated by the Born rule? The rule that tells us to square the amplitude of each component of the wave function to get its associated probability? Surprisingly, the answer is yes, but understanding why requires a deeper look at what probability means inside a branching universe. In classical terms, probabilities are epistemic. They represent a lack of knowledge. But in quantum mechanics, and especially in many worlds, probability becomes ontological. It reflects something about the structure of reality itself. In the multiverse, we are not talking about ignorance of which outcome will happen. We're talking about the distribution of measure across branches, the degree to which different outcomes are realized in the evolving wave function. This measure is not the number of branches. There are infinitely many branches, and even tiny changes can generate new ones. Instead, it's related to the squared amplitude of each component of the wave function. This squared amplitude tells us how much of the total wave function belongs to that branch. In this view, not all branches are created equal. Some carry more weight than others, and that weight translates into the probability that we as observers will find ourselves in one branch rather than another. This introduces a subtle but important distinction. From the outside, from the perspective of the total wave function, all branches are real. But from the inside, from the subjective view of an observer embedded in the wave function, the experience of a particular outcome has a certain probability which corresponds to the relative amplitude of the branch they inhabit. In other words, probability in the multiverse doesn't reflect uncertainty about what will happen. It reflects uncertainty about which branch you will find yourself in. You know all outcomes occur, but you don't know in advance which version of you will experience which one. Before the measurement, you are a unified observer. Afterward, there are many of you, each with a valid, consistent record of one outcome. This might sound abstract, but it matches our experience. When we perform a quantum experiment, flipping a quantum coin, measuring a particle's spin, we still perceive one result. We see heads, not tails. And when we repeat the experiment many times, we observe that the results align with the probabilities predicted by the Born rule. Even though all outcomes occur, the frequencies we observe follow a pattern. This is where quantum decision theory and rationality arguments come into play. Several physicists and philosophers have attempted to show that if we accept the logic of the many worlds interpretation, we can recover the Born rule, the core rule of quantum probabilities, as a natural consequence of rational behavior by agents who know they are part of a branching universe. One of the most prominent efforts in this direction comes from David Deutsch and later refinements by David Wallace. Their approach uses decision theory, the same formalism that underlies economics and probability theory, to ask, what preferences should a rational agent have when making decisions in a world where all outcomes happen, but with different branch weights? Their conclusion is that a rational agent should weight outcomes by the square of the amplitude, exactly as the Born rule prescribes, if they want their decisions to be internally consistent and aligned with long-term expectations across branches. In this view, probability becomes a tool for predicting future self-locations within the multiverse, not an indicator of which outcomes are real. Critically, this perspective allows us to maintain consistency with experimental outcomes. If you repeat a quantum experiment thousands of times, the frequencies of outcomes observed by each version of you across the branches will cluster around the Born rule probabilities. The measure of observers seeing these frequencies overwhelmingly outnumbers those seeing wildly divergent results. In other words, the law of large numbers still holds, not within a single branch, but across the landscape of branches. This has led some researchers to suggest that probability in the multiverse is an emergent property. It's not a fundamental rule handed down by nature, but a statistical regularity that arises from the structure of branching and the evolution of the wave function. Much like thermodynamic laws emerge from the motion of atoms, quantum probabilities emerge from the structure of the multiverse. There's another subtle layer here, one involving self-locating uncertainty. Before a measurement is made, you know that all outcomes will occur, but you don't know which version of yourself you will become. This introduces a form of probability that is not about physics, but about identity. Which future me will I be? This kind of uncertainty persists even in a deterministic theory like many worlds, and preserves a role for probability as a meaningful concept in decision-making. You might wonder, can this kind of reasoning ever be tested? Can we empirically distinguish between interpretations based on collapse and those based on branching? Unfortunately, no known experiment today can definitively answer that question. Both interpretations make the same empirical predictions. But what many worlds lacks in direct testability, it attempts to compensate with philosophical and mathematical coherence. Still, the debate continues. Some physicists argue that without collapse, probability becomes meaningless, while others insist that it gains a more natural foundation. It may come down to what one expects from a theory: absolute determinism with internal measures of likelihood, or a stochastic collapse with irreducible randomness. Many worlds is undeniably deterministic. It does not remove uncertainty from experience. It simply reframes it. From a broader philosophical viewpoint, this has strange but beautiful implications. It suggests that your life path is not chosen at random but realized through structure. Your experience of this outcome and not another is not because others failed to happen, but because you are this version of you. Others, equally valid, equally structured, branch off and continue elsewhere. You are not alone in the multiverse, and yet you are singular within your branch. The probabilities you assign to future events are not guesses, but reflections of where the mathematics says your awareness is most likely to continue. Each moment you live carries with it a set of branches, all real, all evolving, and you inhabit one with a probability dictated not by fate, but by the squared amplitude of a wave function. So yes, in the multiverse, probability still makes sense. It is not diminished, but redefined. It is not erased, but clarified. You still roll the dice, you still make decisions, and you still hope. And through it all, the universe, in all its branches, follows the rules it always has, splitting gently, silently, and endlessly around you. Chapter 8. Why you can't use the multiverse to communicate or travel. The concept of a multiverse often captures the imagination in ways that extend far beyond physics. Popular science fiction explores the idea of people traveling between universes, communicating across timelines, or consciously choosing alternate realities. It's a compelling narrative, one where the multiverse becomes a landscape we can navigate, like cities on a map. But the many worlds interpretation of quantum mechanics, despite predicting a vast multiverse, firmly closes the door on such possibilities. According to the theory, branching occurs continuously and universally, but once branches diverge, they become causally isolated. No signals, information, or energy can pass between them. In a very real sense, these universes are not just far away, they are unreachable, fundamentally disconnected by the nature of quantum evolution itself. To understand why this is the case, we need to examine what happens during quantum decoherence. As we've discussed in earlier chapters, decoherence is the process by which quantum systems interacting with their environment lose the ability to exhibit interference. When a particle, say a photon, becomes entangled with its surroundings, its possible states evolve into separate branches of reality. These branches correspond to different outcomes, such as the photon passing through a slit or being detected at a screen. Once decoherence has occurred, those outcomes are no longer able to interfere with each other. After decoherence, these branches are no longer part of a single coherent quantum system. They are components of the total wave function, yes, but their interactions are effectively cut off. The key phrase here is effectively cut off. In principle, the branches are still mathematically connected as parts of the full quantum state. But in practice, the quantum information that distinguishes them becomes dispersed across so many degrees of freedom that no single observer or apparatus could ever reconstruct it. In quantum mechanics, information is conserved. The overall evolution of the wave function is unitary and reversible. But this doesn't mean that we can reverse decoherence. The information that identifies one branch from another is still present, but it's been smeared out into the environment, scattered among air molecules, photons, atoms, and other particles. Recovering that information would require recombining the entire environment into a coherent quantum state, an unfathomably precise operation that would involve controlling every quantum interaction that has occurred since the branching began. Because of this, you cannot send a message to another branch. You cannot visit a version of yourself who made a different choice, You cannot build a machine to reunite with an alternate outcome. These ideas are not just technologically unfeasible, they're forbidden by the physical principles of the theory. Once decoherence has occurred, branches are locked into their own trajectories, unable to interfere or exchange information. This may sound disappointing. If the multiverse is real, if there truly are countless versions of ourselves living out different futures, why can't we access them? Why can't we benefit from their knowledge or explore their histories? The answer lies in the nature of what branches actually are. They are not places in space, nor parallel timelines running alongside each other in some higher dimension. They are independent, non-interfering components of a mathematical structure, the universal wave function. They do not exist next to each other in any conventional sense. There is no tunnel, portal, or bridge that connects them. The distance is not physical. It is informational, and quantum information is delicate. It cannot be copied perfectly, as shown by the no-cloning theorem, nor can it be transmitted faster than light. These rules apply within a single branch, and they apply doubly across branches. Any attempt to access another branch would require violating these principles. Even if we had an advanced quantum computer capable of manipulating the wave function at large scales, we would still face the barrier of decoherence. The universe does not erase its histories, it just prevents them from overlapping. Let's consider a common misconception: the idea that entanglement could be used to communicate between universes. Quantum entanglement is indeed a real and remarkable phenomenon. Two particles can become linked in such a way that measuring one instantly determines the state of the other, no matter the distance between them. But this effect, while counterintuitive, cannot be used to transmit information. It's statistical and constrained by the laws of quantum mechanics. And crucially, entanglement only works within a single quantum system, a single branch. Once branching has occurred, the systems are no longer coherent. Entanglement does not span universes. So if inter-universe communication and travel are impossible, what remains of the multiverse? Is it just a set of unreachable shadows? Far from it. The multiverse is not there to be accessed. It is there to explain. It provides a framework for understanding why quantum mechanics works the way it does, why probabilities follow the Born rule, why decoherence leads to classical experiences, and why we observe the outcomes we do. In this view, the multiverse is not a playground, it's a foundation. It underpins the universe you live in. It holds all possible histories, all outcomes, all paths. You don't need to travel to it. You're already within it, in one of its infinite branches, shaped by the choices of particles and fields, by interactions and entanglements, by the logic of wave functions and the precision of the Schrödinger equation. To appreciate just how deeply the impossibility of interbranch travel is rooted in physics, consider the idea of reversibility. In theory, quantum systems evolve in a reversible way. But in practice, reversing a system that has undergone decoherence would require you to precisely reconstruct the state of every particle in the environment that interacted with the system. This includes thermal photons, molecules of air, vibrations in nearby materials, the entire quantum state of a macroscopic section of the universe. This is not just hard, it is fundamentally beyond the realm of feasibility. In fact, if such reversibility were possible at will, it would upend the arrow of time itself. The increase of entropy, the basis for time's flow from past to future, relies on the practical irreversibility of decoherence. In attempting to unbranch the universe, you would have to reverse not only quantum processes, but the very thermodynamic direction of the cosmos. That is not a road physics allows us to walk. And even if you could achieve this, if somehow a branch were recohered, it wouldn't bring you into contact with a different you. Instead, it would recreate a quantum interference pattern, merging parts of what was previously separated. The result would not be dialogue or visitation. It would be a statistical artifact, visible in a lab experiment, not lived as an experience. Reality is not a film to be rewound or a network to be navigated. It is an evolution of states, bound by consistency and thermodynamic directionality. These constraints arise not from a lack of imagination, but from the internal logic of quantum theory itself. The same laws that allow branching, the beautiful, orderly evolution of the wave function, also seal those branches off from one another. They are not walls we can break. They are boundaries written into the equations of the universe. Yet, despite all this, the multiverse is not meaningless. In fact, its very inaccessibility is part of what makes it so compelling. The fact that we can't send messages or build bridges between branches doesn't render them any less real. It simply means we are confined, not by illusion, but by coherence. Our experience is one thread, one timeline, carved out of a much richer fabric. From a philosophical perspective, this invites reflection. What does it mean that countless versions of you exist, making different decisions, following different paths, and yet none can ever reach across to another? It means that your reality, however solitary it feels, is part of a vast, deterministic tapestry. You don't have to reach the other branches. Their existence gives context to yours. The probability of your path, your life, your thoughts, emerges from the branching you never see. In this way, the multiverse is not an invitation to explore. It is a reminder to observe. Not outward into unreachable spaces, but inward, into the strangeness of your own presence in a universe built from branching possibilities. You are not trapped in one outcome. You are that outcome. You are not missing out on infinite lives. You are living one of them fully, governed by rules that permit all others, even if you can never know them. So no, you can't use the multiverse to communicate or travel, but you are shaped by it. Your very sense of certainty, your unique trajectory through time, is a consequence of its branching. And through that lens, even the quietest choices carry cosmic weight, because they define the path you will never leave. Chapter 9. Can we ever test the many worlds hypothesis? The many worlds interpretation, MWI, of quantum mechanics presents a bold and sweeping vision of reality, a universe that continually branches into countless versions, each capturing a different outcome of every quantum event. It resolves the measurement problem without invoking collapse, treats the wave function as fully real, and aligns seamlessly with the deterministic Schrödinger equation. But for all its internal elegance, MWI faces a difficult and enduring challenge. Can it be tested? Can we, as observers confined to a single branch, ever hope to gather experimental evidence that supports or refutes the existence of all the others? This question strikes at the heart of what it means for a scientific theory to be meaningful. In physics, we generally demand that a theory make testable predictions, that it risk being proven wrong. This criterion, known as falsifiability, helps distinguish science from speculation. So does MWI meet this bar? At first glance, the answer appears to be no. All versions of quantum mechanics, whether they include collapse or not, produce the same statistical predictions for observable outcomes. Whether we interpret a quantum measurement as collapsing a wave function or as branching into multiple worlds, we still expect the same pattern of results in experiments. So long as MWI and collapse-based theories are empirically equivalent, it seems we have no way to decide between them. Yet the situation is more subtle than it first appears. While it's true that MWI doesn't make different predictions for standard measurements, it does impose a radically different ontology, a different account of what exists. And this matters because it opens the door to indirect tests. We may not be able to see the other branches, but we can ask whether their existence helps us understand phenomena more coherently, or whether alternative theories introduce unnecessary complications. One area where this becomes clear is the question of simplicity. MWI requires no additional postulates, no rules for when and how collapse occurs, no special role for observers. It treats all physical systems equally and obeys the same universal law, unitary evolution. In contrast, collapse-based theories must specify when collapse happens, what constitutes a measurement, and how probabilities emerge from a single outcome. These added rules are often seen as ad hoc, lacking a firm physical basis. By this metric, MWI scores well. It doesn't explain more, but it assumes less. This parsimony is a kind of explanatory power, a way of saying, let the equations speak for themselves. And in science, fewer assumptions are often preferred. Another approach to testing interpretations is to look at how they influence new lines of research. In recent years, interest has grown in exploring whether collapse is a real physical process. This has led to the development of objective collapse models like the Ghirardi-Rimini-Weber (GRW) theory and Penrose's gravity-induced collapse. These models suggest that wavefunction collapse is not just a convenient rule, but a genuine, measurable event, one that occurs spontaneously under certain conditions, even in the absence of observers. Such models make predictions that deviate, however subtly, from the standard quantum formalism. These deviations can, in principle, be tested. Experiments have been designed to detect spontaneous collapse, such as looking for unexplained heating in isolated systems or tiny, random jitters in the motion of particles. So far, no deviations from standard quantum mechanics have been observed. Experiments involving macroscopic superpositions, such as Schrödinger cat states in superconducting circuits, show no signs of collapse. The systems evolve as predicted by unitary dynamics, decohering naturally without the need for a reduction mechanism. These results are not direct proof of MWI, but they do erode the case for its alternatives. Another frontier is quantum computing. Quantum algorithms such as Shor's and Grover's are designed to exploit superposition and interference. Some researchers argue that the power of quantum computation makes more intuitive sense under MWI, where all computational paths are physically realized in different branches. From this perspective, a quantum computer isn't solving problems in a single world. It's solving them across a vast, branching multiverse. While this view is interpretational, it aligns cleanly with the structure of the theory. Still, MWI faces a significant hurdle. Its core premise, the existence of other branches, seems inherently unobservable. By design, the branches are decohered. They don't interfere. They don't leave direct traces in our world. This makes experimental confirmation deeply problematic. To address this, some physicists have proposed thought experiments involving quantum revival. In principle, if one could isolate a quantum system perfectly and reverse the effects of decoherence, it might be possible to bring previously decohered branches back into contact. This would produce interference between histories, a kind of echo of other branches. However, the requirements for such an experiment are beyond what any laboratory can currently achieve. Isolating a system from all environmental interaction for more than a few microseconds and reversing it with perfect fidelity is a technical challenge orders of magnitude beyond our current capabilities. That said, this line of thinking remains valuable. Even if we never achieve total quantum revival, the search for interference effects or anomalies in decoherence dynamics keeps the discussion alive. If any deviation from standard predictions were found, it could either rule out MWI or give it indirect support, depending on the nature of the anomaly. Another strategy is to evaluate interpretations through consistency and conceptual coherence. MWI doesn't suffer from the measurement problem. It doesn't need to define what counts as an observer or when collapse happens. It doesn't violate unitarity, the principle that quantum evolution is deterministic and reversible. These are not minor conveniences. They are indicators of internal consistency, which, in a field as mathematically precise as quantum mechanics, carry real weight. At the same time, MWI demands a major philosophical shift. It asks us to accept that the universe is vastly larger, or at least more intricate, than what we observe. It challenges the notion of a single, objective reality shared by all observers. It implies that our experience is just one thread among countless others, and that everything that can happen does, just not all in the same branch. This view is unsettling for many. It seems extravagant. It feels untestable, but perhaps the real challenge is not physical, but cognitive. The resistance to MWI may stem not from flaws in the theory, but from the sheer strangeness of its implications. Humans are wired to think in terms of single histories, definite events, and singular selves. The universe that branches endlessly, where every possibility is realized, runs against our deepest intuitions. And yet, physics has repeatedly shown us that nature does not conform to intuition. From relativity to quantum entanglement, reality has always been stranger than it seems. Perhaps the many worlds interpretation is simply the next step in that progression, a way to take quantum mechanics seriously and literally. Can we ever test MWI? In the strictest sense, perhaps not. But in another sense, we already are. Every time we perform an experiment that confirms quantum mechanics, every time a macroscopic superposition decoheres as predicted, every time a quantum computer runs an algorithm that classical systems cannot match, we affirm the consistency of a universe that follows the rules MWI describes. And so, the verdict may not come in a single dramatic discovery. It may emerge gradually as other interpretations falter, as collapse models are ruled out, as the elegance of many worlds becomes harder to ignore. In the end, we may come to accept MWI not because we found a door to another world, but because we found no reason to believe they aren't there. We may never observe the branches, we may never touch them or cross into them, but the universe, silent and precise, continues to evolve as if they are real. And if the equations say they are, if they require no extra assumptions, no magical collapse, no hidden variables, perhaps that is enough. You live in one branch, you remember one past, but the laws that shape your experience shape all the others too. The multiverse doesn't need your permission. It needs only your curiosity. In the quiet rigor of quantum theory, many worlds remain standing, not as a fantasy, but as a natural extension of the mathematics. It may never give us branching machines or glimpses into alternate selves, but it offers something subtler, a framework in which the strangeness of quantum mechanics becomes inevitable rather than mysterious. It invites us to view probability as identity, observation as entanglement, and choice as structure. And in that light, every experiment is already a test, not of other worlds, but of the one we find ourselves in. Chapter 10. When physics suggests more than one reality. In classical science, the notion of reality was simple and singular. There was one universe, governed by absolute laws, unfolding in a fixed and predictable manner. Observation revealed a world out there, objective, shared, and singular. But the advent of quantum mechanics shattered that picture. It replaced certainty with probability, determinism with amplitude, and clarity with superposition. As physicists explored this new landscape, it became clear that reality, at least as described by the mathematics of quantum theory, might not be one, but many. And while interpretations differ, the formalism itself seems to whisper a profound possibility that more than one version of reality can exist, not just theoretically, but simultaneously. The mathematics of quantum mechanics does not demand collapse. The wave function evolves smoothly and deterministically, spreading across all possible outcomes. When we observe a system, the equations do not pick one result, they retain all possibilities. It is our interpretation, not the theory itself, that insists on a singular experience. This is where the many worlds interpretation finds its power. It does not rewrite quantum mechanics. It simply takes the wave function at face value. It says, if the math includes all outcomes, then so does the universe. No special rule is needed to select a result. Instead, reality splits, not visibly, not violently, but mathematically, branching into versions, each consistent, each isolated, each real. That idea that the universe may not reduce itself to a single outcome is one of the most radical in the history of science, but it is also one of the most parsimonious. It removes the need for mysterious collapse mechanisms, observer-centric rules, or hidden variables. It retains the purity of the equations and lets them describe the world in full. And while the many worlds interpretation is the most direct expression of this idea, it is not the only place where physics hints at multiple realities. In cosmology, inflationary models suggest the existence of bubble universes, isolated regions with different physical parameters. In string theory, the so-called landscape contains a vast number of possible vacuum states, each potentially corresponding to a different universe. Even black hole physics, with its paradoxes of information loss and firewall hypotheses, occasionally suggests observer-dependent realities that differ in more than just perspective. In each case, the math points toward multiplicity, not because physicists want it to, but because it is the simplest, cleanest way to resolve contradictions. More than one reality is not a poetic flourish. It is a solution, one that fits the data, preserves the laws, and maintains internal consistency. Let's explore one of the most striking examples where physics seems to hint at a multiplicity of realities: the double-slit experiment. When a single electron is fired at a screen with two slits, it creates an interference pattern, as if it passed through both slits at once. But when a detector is placed to observe which slit it goes through, the pattern disappears. This phenomenon is not limited to electrons. Photons, atoms, even some molecules exhibit the same behavior. Standard interpretations say the act of measurement collapses the wave function into a definite outcome. But many worlds avoids that collapse altogether. In this view, the electron goes through both slits, but in separate branches. One version of you sees it go through the left slit, another the right. The interference pattern arises from the combined mathematical structure of the full wave function, a structure that reflects more than one reality at once. Another striking case comes from quantum entanglement. When two particles are entangled, a measurement of one instantly determines the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein called it, violates classical intuitions. But in the many worlds view, no action at a distance is needed. All outcomes occur. Each branch contains one outcome for each observer, perfectly correlated without the need for non-local influence. Even the concept of wave function collapse becomes unnecessary. Collapse is not observed directly. It's inferred as a postulate to explain why we perceive definite outcomes. But if each outcome exists in its own branch, then nothing needs to collapse. Instead, reality expands, smoothly and inevitably, into coexisting versions. Consider now how cosmology deepens this idea. During cosmic inflation, the universe expanded at an exponential rate. Quantum fluctuations during this phase were stretched to cosmic scales, seeding the structure of galaxies and clusters. But these fluctuations were quantum in origin, and thus, under many worlds, every possible configuration of these fluctuations branched into its own macroscopic universe. What we call the observable universe is simply one realization of many. Furthermore, if eternal inflation is true, then inflation never stops globally. It ends only locally, forming bubble-like regions where expansion slows and space cools into matter and energy. Each of these bubbles could have different physical laws depending on the outcome of symmetry-breaking processes. These are not science fiction realms. They are allowed, even expected, by current models of inflation and quantum field theory. String theory adds another layer. With its extra dimensions and multitude of possible compactifications, it doesn't yield one unique prediction for the shape of space-time or the constants of nature. Instead, it gives rise to a landscape of solutions, possibly numbering 10,500 or more, each corresponding to a different way the extra dimensions can fold. If our universe is just one point in this landscape, then countless others may be equally real, differentiated by initial conditions or field values. And then there's black hole complementarity. To resolve the information paradox, some physicists propose that information is both reflected at the event horizon and passes through it, depending on the observer. This suggests a kind of observer-dependent reality. Again, more than one version of events must coexist, not just in abstract mathematics, but in the physical structure of quantum gravity. All of these theories point to a shared theme: the possibility, even the necessity, of multiple coexisting realities. Not because they are philosophically appealing, but because they resolve puzzles that otherwise seem intractable. Critics often argue that these ideas are extravagant, that invoking more than one universe violates Occam's razor. But Occam's razor does not favor fewer entities in general. It favors fewer assumptions. If one universe requires arbitrary collapse rules, hidden mechanisms, or observer-dependent physics, while multiple universes require only following the math as written, then the latter is the simpler, cleaner theory. Indeed, the true extravagance may be in denying what the equations plainly say. If the wave function evolves unitarily, if it contains multiple outcomes, and if no collapse mechanism has ever been observed, then perhaps we are not being cautious by rejecting the multiverse. We are being evasive. But what does this mean for us? If physics suggests more than one reality, how should we live in one? It means that our experience, vivid, singular, and seemingly unique, is one branch of a much larger process. The world you know is not false. It is not diminished by the existence of others. It is simply your version, one path through a quantum forest. And while you may never cross into another branch or speak to another version of yourself, the structure of reality is shaped by their presence. The probability you assign to events, the patterns you see in randomness, the very sense of causality you experience, all emerge from the interference, coherence, and separation of other possibilities. Your memories are real, your choices matter, and your path is meaningful. But it is not the only one. Physics suggests that reality is not a singular monolith, but a living lattice, branching, unfolding, evolving. Perhaps this does not diminish reality. Perhaps it completes it. A single world is elegant. A multiverse is inevitable. In the end, physics doesn't ask for our belief. It asks for our understanding. And when the equations point toward multiplicity, we are faced not with fantasy, but with a broader form of realism. One that includes your reality and all the others. Not as science fiction, but as the scientific consequence of taking quantum theory seriously. We may never step between worlds, but we may finally accept that we are part of a universe rich enough to hold them all. If you're still awake, thank you for journeying through this quantum landscape with me. The path you took here may be one of many, but it's the one that matters right now. And if sleep hasn't found you yet, another universe of thought awaits. So feel free to let the next video guide you deeper into the cosmos. Sweet dreams among the stars, dear friend.